As introduced, basically I'm a textile engineer, and for the textile application, the statistical knowledge is very essential. That's why I developed a lot of interest in statistics, and I applied them also in many areas, and of course I interacted with the industry so that they can also understand and apply in a proper way, and that will help them in improving their performance. I will just explain to you what is the fundamentals of statistics that might create some interest among the participants, and of course they could gain some more knowledge. And to gain more knowledge, you have to refer many books. One of the books just I have mentioned as a sample. This is a book by Montgomery. He has written a lot of books actually on statistics, and this is one of the books. I would request the participants, if they are interested in statistics, to go through all the books written by Dr. Montgomery. So now coming to the topic, actually, every phenomenon that is taking place around us can be totally classified into two. One is the deterministic phenomenon, and another is the probabilistic phenomenon. And of course, the deterministic phenomenon is defined as if go for repeated measurements under identical condition, it will give the same value. So that we call the deterministic phenomenon. Example of the deterministic phenomenon is the measurement of, say, atomic weight. Anytime you measure, it will give the same value. Even most of you might have done the titration in the chemistry laboratory. So we will go for the concurrent values actually. We will not take the average value. We will go for the concurrent value. That means the titration of one chemical with another chemical is in the volume required to get totally reacted. It will be a single value. It will not be a different value. So that's why we go for the concurrent values. And these are the examples for the deterministic phenomenon. And coming to probabilistic phenomenon, it's actually curious that even if we repeat the measurement under identical condition, it will not give the same value. So that's a problem with the probabilistic phenomenon. But of course, most of the phenomena taking place around us is the probabilistic phenomena. So we have to put up with this and try to get some useful information from this probabilistic phenomena. All of you know that if you look around us, there are many things actually. For me, actually, it's a table, a telephone, a printer. It may look all stationary, but actually you all know that it contains a lot of moving particles. You all know that, isn't it? Every matter is made out of atom. In atom, the electrons are moving. So it is a myriad of moving particles. All the matter consists of moving particles. And if you know what happens to the electron, nobody can predict the exact position of the electron at a particular time. It is a probabilistic phenomenon. So every matter is made out of electron, and which is decided by actually some probabilistic theories, not by deterministic theories. So this just to make you understand the importance of the probabilistic phenomena. We cannot predict what happens actually in all the cases. So another classical example is actually tossing the coin. So when you toss the coin any number of times, you cannot predict what will happen next. So it may either head or tail or head or tail, isn't it? Only the two outcomes. We don't know what will happen when we toss the coin. So this is generally is a classical example for a probabilistic phenomenon. Those who attended the classes on statistics, so this example would have been repeated many times. Of course, so there are variables. You know that the temperature varies, pressure varies, but with respect to the random variable is the variable associated with all the probabilistic phenomena. So the main feature of the random variable is its value cannot be predicted in advance. So if you know that the famous equation PV equal to RT, pressure versus pressure into volume equal to R into T. So in the equation, or if you take the famous Newton equation, F equal to mass into acceleration, if we know all other parameter other than one particular parameter, we can predict exactly. We can predict. So if we know the mass and acceleration, we can predict exactly what will be the force. Similarly, if we know the temperature and the pressure, we can find out the volume exactly. These are the cases of a deterministic phenomena. But in the case of probabilistic phenomena, you cannot predict what will be the outcome in the probabilistic phenomena. So that's a problem actually, and that is the main issue all with this probabilistic phenomena. But one interesting feature is it exhibits a recognizable pattern actually that is stable for a large number of observations. So I given one a simple example of what is a pattern. Actually, the frequency of different values will exhibit a recognizable pattern that is stable. You see that frequency versus the value of the variable, it will have a recognizable pattern that is stable over large number of observations. Large number of observations. That is another important point actually. So this is the regularity. So even though we cannot predict what would be the value of the individual value, we are in a position to predict the frequency, or in other words, the probability of occurrence of a particular value. So that stable pattern actually has made us or permitted us to go for a systematic analysis of the random phenomena. If we don't have this kind of stable pattern, the whole subject of statistics could not have evolved actually. So we could not do anything, we cannot do any analysis. So this is a fundamental concept that the frequency of occurrence of individual value will have a stable pattern that only permits us to go for all kinds of analysis. And I have shown only one simple model. It's not the only model for the random variable. Depending upon the behavior of the random variable we come across, we use, it will exhibit a different pattern. So this is one of the patterns, just for an example I have shown. So now this is a comparison between the deterministic and the probabilistic variables. So far what I discussed about that, you could see that the deterministic variable can be completely explained by assigning a single value. So if you want to know what is the atomic weight of carbon, if I say that it is 12, that ends the explanation. No more explanation is required actually. But unfortunately, with respect to the probabilistic variable, it cannot be defined by a single value. It requires a distribution. The distribution is something like this, what I have shown here. So any random variable requires this kind of distribution to understand completely the behavior of the random variable. So if we take the example of the strength of any material, the strength of any material cannot be assigned by a single value, because it may vary from a lower value to a higher value, and the frequency of occurrence of each value also would be different. So this can be explained only by assigning a distribution. Now you all are familiar with this kind of statistical models. So I've shown only just two models for an example. So the Poisson model and the normal model. You know, in the Poisson model, say, to give an example, say how many number of vehicles will cross a particular point in a road. If you want to know that, how many vehicles will cross a particular line in a road, there is no a single value. Nobody can predict what exact number of vehicles would cross that particular point. It requires a distribution. That means it may range from 0 to 100 over a period of time. So from that a distribution only we can understand how many vehicles would cross, and from that only we can derive some useful information. So similarly, there are examples for a normal model. So there are many standard distributions like normal, Poisson, binomial, variable, exponential, and geometric. So there are many distributions available. So those who are experimenting with the probabilistic variable should be in a position to choose a right distribution and apply them for his experimentation. So choosing the right distribution, that depends upon the behavior of the random variable you deal with. In some cases, it can be exponential. Some cases, it can be normal distribution. So you have to choose the right one. So to sum up what I have told so far, so there is some echo coming. Hello.
Sir,
Yes,
I'm checking,
sir.
sir. Our server,
Good morning, ma'am.
Yes.
no, no. Mangesh Acharya, sir, you have to mute. So now it's okay, sir.
Okay. So the statistical analysis requires the statistical model. So without the statistical model, we cannot go for any analysis. And from the model only, we can derive some objective conclusion. So any model, I'm just going back. So if you see here the normal model, if you could see there are two parameters. One is mu and the another is sigma. You could notice that. So mu, all of you know that it is a common one, it is a mean, and sigma is the standard deviation. So if we have a set of values of a random variable, and if you could calculate the mean and the standard deviation, so from this equation that is given, we can totally analyze and understand the behavior of the random variable. Again, I repeat, whatever the random variable we have, say a strength of a material, if we take an example, how the strength of the material values varies, how many of them will be above, say, 400 or less than 300, something like this. If you want to know that, so you should have this equation. So to completely understand the equation, we require the values of the two parameters. We call this parameter, the mu and sigma, the mean and the standard deviation. So these are the basic requirements. Once you know that, we can finally and completely understand the behavior of the random variable we deal with. So the main task of the experimenter is estimating the value of the parameters from the incomplete data. Again, this is a most fundamental point as far as the statistical analysis is concerned. We all know that the population would be very large. You may not be in a position to find the value of all the material in the population. It may not be possible. It may contain 1 million specimens. So we cannot find the value for each and every one of the 1 million specimens. So in that case, what we do, we take a sample and estimate these two parameters. So mu and sigma are the parameters we require. And we could estimate, you understand the difference between determine and estimate. Determine means you find the exact value from the total population. But estimation is estimating the value of these two parameters from the incomplete data, from a small size of the sample. So that's the problem. So what will happen, the estimated value, say if we have a sample and sample mean is assume x bar, and the x bar will not be equal to the population mean mu. So there would be an error. So the mu minus x bar is the error. So that normally we call it as the sampling error. So the error caused by incompleteness of the data. So if the data is complete, the error would not have happened. So because of the incompleteness, there is a sampling error. All of you should recognize and accept and understand the sampling error. So whenever we test a sample, that value we get is not the correct one, not the true one. It's only estimation of the true value. So there is always an error implied in our estimation. So that error all depends upon the sample size we calculate, we use. N is the sample size. So sometimes we may use 10 tests, sometimes we may use 100 tests. So that number of tests would decide the error. You see the equation. So Z is the standard normal variable, so that you can obtain from any normal table. And CV is the coefficient of variation of the variable under consideration. And the another one is the error percentage we can admit. So that is the sampling error percentage we can admit. If you want to admit, you see that 0% error, the N would be infinity. So only when the N is infinity, that means the whole population is checked, then only the error percentage would be 0. Otherwise, there would be some error. So if the N is 10 or 100, accordingly there would be some error percentage in our estimation. So depending upon our requirement, I would say that there are two roles actually. One is the role played by the statistician, and another is the one played by the real experimenter. So the statistician can give the equation actually, and the experimenter only should decide what should be the sample size depending upon the accuracy he requires in his prediction. So statistician cannot do that. So sometimes you may require 1% error, some may admit 10% error. So depending upon that, the sample size can be decided. So there is no common value for the sample size. It's not 20 or 30. We cannot generalize the sample size for all the cases. It varies from cases to cases depending upon the CV percent of the variable. If the CV percent of the variable is higher, the sample size has to be higher. And similarly, if the error in prediction should be lower, then also the sample size has to be higher. So the sample size has to be decided based on our requirement, based on the accuracy we want to apply. And of course, these implications that mentioned here are very, very important. That so to find out the population mean, as I already told you, we could have taken a sample, and from the sample of say size 30, number of tests say 30, we would have found the mean, the sample mean. So the sample mean is different from the population mean. So the sample mean calculated itself is a random variable. I told the definition for the random variable, that means its value cannot be predicted. And similarly, if we take a sample of 30, so what would be the mean? Nobody can predict. It itself is a variable. And it need not be equal to the population mean, what we want to estimate. So the first statement is very important. The sample mean, what we calculate, is itself is a random variable. And it need not be. Sometimes it may be, so, it is a very rare probability that it may equal to the population mean, but it's very rare. It need not be equal to the population mean. And again, you see that there is always an error involved in the estimation, and the maximum error we permit is E%. So once you decide about the E%, and from the formula given as shown earlier, you can find out the sample size, and if you have chosen the sample size, so the error will be limited to E%. Based on the sample size will decide the error you commit. So it will be limited to E%. And the maximum error will be limited to E% on 100 minus alpha percentage occasions out of 100 occasions. So if alpha percentage is 5, if we assume that, then on 95 out of 100 occasions, the error percentage will be limited to E%. And the remaining 5 occasions, the error percentage will be more than E%. This is another important observation and point everybody should notice. Only if you conduct experiments for 100 times, only 95 times the error will be less than E%, and the remaining 5% the error will be more than E%. And again, one will not know on which occasion the error is more than E% or less than E%. So we have some value of sample mean, and we can say that there is a 95% probability that, or 0.95 probability that the error will be less than E%. That means what the value we have, the error need not be less than E%, and sometimes it can be more than E% also. So these are the implications. So just to summarize whatever I already told about the sample size. So the selection of sample size is very, very critical, because it's required to estimate the population parameter, and the population parameters is used in the the distribution what we adopt. From that only we can fully understand the behavior of the random variable we consider. So in choosing the sample size, so it should be the correct one we have to choose. Even after choosing the sample size, it's not a rest assured that whatever the sample mean we calculate, error percentage will be less than E%, and it need not be. Some of the cases it can be more than that also. All uncertainty is involved. But what we do in statistical analysis is we understand the value of the quantum of uncertainty. So that the 5% uncertainty, so we can quantify the level of uncertainty in our statistical analysis. But there is always uncertainty. We cannot eliminate the uncertainty in our statistical analysis. If you want to eliminate, as I said, that the sample size should be infinity, or it should be the whole population. Normally, it may not happen. And of course, you are also familiar with the testing the hypothesis. When we have the sample, whether it mean is mu1 or it is greater than mu1 or not. So for that purpose, this formula that gives the calculation of the sample size. So mu1 is the mean of the correct population, and mu2 is the mean of the wrong population. So we test whether whatever the sample we have with us, it belongs to the correct population or not, based on making the null hypothesis and the alternate hypothesis. So most of you might be familiar about that. And what I'm telling here is the calculation of the correct sample size. So that will limit the error. So here alpha and beta are the error actually. So this graph explains what is Z alpha and what is Z beta that is obtained from the normal distribution curves. And so these are the two errors actually, alpha error and the beta error. And another name is type 1 error for alpha is the error. That means we reject the null hypothesis, and when the actual mean is mu1, we say error. So from the sample what we have, and we come to the conclusion that the population mean is other than mu1. So because that's an error, isn't it? So actually the sample belongs to the population of mu1, but after carrying out the test, we say that the sample doesn't belong to the population with the mean mu1. That means it's an error. So that error is alpha percent. Another error is type 2 error, that is a beta percentage. That is, we accept the null hypothesis. That means we say that what the sample we have from the population of mu1, but actually it belongs to the population of mu2. So any decision you take, isn't it? Either we accept the null hypothesis or reject the null hypothesis. Either way, we commit an error. As I already told you, we cannot escape from committing an error in statistical analysis. What we can do is we can quantify the error, alpha percentage or beta percentage. So if you want to reduce the error, accordingly, we have to choose the sample size. So sample size is the only parameter. So that will help us in reducing the error. Of course, larger the sample size, less the error. But again, we cannot keep on increasing the sample size, because there are a lot of difficulties involved in increasing the sample size. So one is, if it is a destructive test, we will be destroying the material. And the second is there will be a lot of cost involved in carrying out a large number of tests. Cost and time are involved. So that's why we should choose the sample size. It will be optimum one. So it is neither large or low. It should be an optimum one, and that the information we derive from the sample size would be useful to us. It's another case actually. When you buy a lot, say a lot of material, say 1 lakh material, and what we do normally, the buyer would choose the material at random, say n number of material he choose, and test for it and find out the number of defectives. So if the defective is less than C, so in the equation I mentioned that if the defective is number of defectives less than C, he may accept the lot. If the number of defectives is more than C, he will reject the lot totally. So because again I repeat, you cannot test the whole lot. Only a small number only he will test and find out the defectives. If the number of defectives is less than this value or that value, based on that you will make a decision, a critical decision, either accepting the lot or rejecting the lot. So the sample size is also now becomes very important. So this is a formula used for acceptance of a lot. Here two parameters, one is the sample size and another is the acceptance quality level, as I already mentioned, C. So based on the C value, if it is less than C, we will accept. More than C, if it is defective, actually, we will not accept. And here again, you could see the alpha and beta. The alpha and beta are the things I already told you. These are the error. So if you want to reduce the error, so naturally you have to go for large sample size. And using the value, we can calculate the acceptance quality level and the sample size, and we can go on going for the testing the acceptance of a lot. So the different cases, I just to estimate the population parameter, I given one formula, and the another is acceptance of the sample. I given a formula to find out the sample size. And the third case is when testing the hypothesis, null hypothesis, alternate hypothesis to accept or not. Again, so we have to do for some sample experiments and what should be the sample size. In all the three cases, I told you the importance of the sample size. So that selection of sample size is very critical. That's why I'm upon the point again and again. I know most of you are academicians, basically they're all faculty members. Those who got experience in an industry. So in the industry, the controlling the process is the most important one. So now we cannot say that we are not familiar with the process control. It should be, because every faculty should be attached with the industry, and you should know the operation that's being carried out in an industry. And while controlling the process, what should be the sample size? So you all know that this is the control chart. So any value falls outside the UCL or LCL. UCL is the upper control limit and LCL is the lower control limit. If any value falls outside, then we come to know that the process is out of control. That means to solve the process, you have to go for a correction. If you don't do that, we will make a product all are defective, isn't it? Then when it is defective, we have to sell them as seconds, or we have to carry out some corrective measures, then only we can sell them. So controlling the process, continuously controlling the process is the most important thing. So again, here also the process, as it goes, we will not test all the specimen. We will take a sample and test them. And this is the sample size, say we have decided again based on the alpha and beta values. And we can find out whether the process is in control or out of control. As told already, even when we have a statistical process control exercise, it's not without error. There would be some error. So the error, actually what we do, the error that what we may commit is, so when we find the mean of the sample, if the mean falls outside the UCL, we may come to the conclusion that the process is out of control. But actually the process may be in control. So we may do unnecessary correction. This is one type of error. Another error is the value in the mean may fall within the two limits, upper control limits and the lower control limits. And we will be under the assumption that the process is in control. But there is a possibility that the process might have been out of control. So these are the two types of error we commit. And I repeat that you cannot escape from either of these two errors. So only the sample size will reduce the percentage of error. So the selection of the sample size will help you in arriving at the correct the percentage of the error. Otherwise, we cannot avoid the two types of error. Normally, we come across either accepting a lot or testing the hypothesis or while controlling the process. It will happen actually. So these are the some rules. So how to come to the conclusion that whether the process is in control or out of control. Of course, these are all standard points are available in the textbook. So as I said that sometimes we may carry out some correction, understanding that the process is out of control. Actually, it's a wrong signal. It's a wrong signal. The process is in control, but we go for a correction. So how many tests we will carry out before we come to a wrong signal is given by the formula actually. 1 minus alpha percent. So if the alpha percent normally in the 3 sigma level, it is 0.0027 actually. So if you substitute that value, you will find that around 370. So in a 3 sigma control process, actually normally 1 in 370 observation, 1 in 370 observation would give you a wrong signal. So we cannot avoid that. So 1 in 370 observation would be a wrong signal. So we cannot avoid that. We have to put up with that. And the another is when the process goes out of control, we should come to know immediately. In the first observation or the second observation itself, we should come to know the process is going out of control. So if it is left as it is, then it will try to produce the defective materials. So within how many observation we can come to know that the process is out of control is given by this formula. So 1 divided by 1 minus beta. You know what is alpha and beta? I already told you. And in the normal distribution diagram, you can understand the position of the value of this, the Z alpha and Z beta. So alpha and beta are the two important parameters. They are error actually that decide, and that actually that only an experimenter has to decide what should be the alpha and beta value. So the statistician will not tell you choose this alpha and this beta. It should be chosen by the experimenter or the operator. If you see here the selection of alpha and beta, so the cost of investigation and correction of the process in response to out of control signals, and this cost influences the selection of alpha value. So when the process goes, isn't it out of control, you have to go for some correction, isn't it? So what is the cost of investigations involved? So if the cost of investigation, the test, as I told you, you select the sample size, say the n is some 50 or something like that, the sample size, we carry out some 50 tests. So it will involve some cost. And after that, we have to correct the process, finding that the process has gone out of control. If you know, you come to know that, and you have to correct the process. So there is cost of investigation and cost of correction. So if these two values are very high, actually, then the alpha value has to be lower, actually. So that these two parameters, cost of investigation and correction, will decide the value of alpha. And similarly, the cost associated with the non-conformity product. So if you produce a wrong product, if the process is not controlled, if it continues to produce some wrong material, then there is a cost associated with the non-conformity product. Either we have to sell them at seconds, or we have to go for some correction of the material. So that cost will decide the beta value. So either as an experimenter or an engineer in a process, you all know that the cost of investigation and the cost of correction, and of course the cost associated with the non-conformity product. So if you know these costs, and based on that only the alpha and beta value should be decided. Once the alpha and beta value are decided, then we can, from the formula I shown, isn't it? You can choose the sample size, that is n. So that is the important point actually I want to convey to our participants. It's not that there's any sample size we can choose, and of course when we carry out research work, we are not worried about the cost involved actually, generally, but in the process, the continuous process, the profit all depends upon the cost. So in an industry, the cost is very important. Those who are working in the industry, those who are giving some consultancy or working in association with the industrial process, should be very critical about knowing the cost of this investigation, correction, and the non-conformity. And based on that, you have to choose alpha and beta. But since I am also associated with the textile industry for many number of years, and I could say that many people actually choose this alpha and beta value arbitrarily, as these values are given in the textbook. They choose at random and give the value and ask us to calculate this and that value in the problems actually, but that will not be helpful. So again, I could say that why statistical process control or applications are not finding useful application in the industry is because of not properly choosing the alpha and beta value. And everything boils down to the cost. So the cost is the important for the industry. So those who are working in the industry or in the associated with the process, and you can also tell the point to your students or other colleagues that the success of application of this statistical process control depends upon calculation of alpha and beta, or selection of alpha and beta. That finally depends on the cost involved. So we have to calculate the cost, and accordingly you have to choose. This is a point I'm repeating again and again, and this is a point not generally told in the classroom. So another important topic I think that will be useful to our faculty member is the experimental design. So in the experimental design, actually we have to develop a model, normally a regression model, involving the input variable and the output response. And this regression model is used for prediction or process optimization or the process control. These the important operation: prediction, process optimization, and the process control. So for these three, we require model. So the model is nothing but the regression equation. As I said, that the relationship between x and y. The x is the random variable, or the independent variable. Y is the dependent variable, that is the response. X is the different variables or the parameters we want to control, say temperature, pressure, or something like this, that is X. Y is the output, say some concentration or density or something like this we want to control. So this equation y on x, that is the regression of y on x, is normally used for optimization or prediction or controlling the process. So if you have the equation, that equation will help in identifying the most influential variables. We may have many number of variables, 5 or 6 variables, but all of them may not influence the outcome y in a significant way. So we have to choose the most significant variable that will influence the response. And of course, once you have chosen those influential variables, next is the level of these variables. Whether we have to keep the temperature at 30 degrees Celsius or pressure at 1 bar or something like this. The level is very important. Those level which would give the most desirable value for y. So one is first selecting the most influential variables, and second is selecting the level of the variables. So once you do that, the process would give the best desirable value. And for this, we require this regression equation. Without the regression equation, we cannot obtain these two important observations. And all of you are familiar, this is one of the regression equation. Of course, the second order polynomial equation, y is the response and x is the variable, and beta is the regression coefficient that one has to find out from the experimental design. So the beta has to be estimated by conducting the experiments. So while conducting the experiments, these are the three important points to be noticed as far as statistical experiments are concerned. So we have to replicate the experiments. Replicate is we have to repeat the experiment for more than once. So this is an essential part in any statistical experimentation. So that will estimate the variance of the random error. And the second is randomization. Of course, we have to allocate the experimental material in order in a random manner. So that's why the variation associated with each experimentation would be distributed at random. And blocking is another thing. So if you have some 4 or 5 units, all the experiments should be conducted in all the 5 units. We cannot distribute the experiments selectively to different units or different blocks. That will cause some nuisance value. So that can be eliminated. So replication, randomization, or blocking are essential points to be considered while we go for experimental design. And of course, the number of experiments, so the minimum number of experiments we have to conduct should be the minimum number of coefficients to be estimated. So it is in the case of the second order polynomial equation, if you consider for 3 variables, so there would be some 10 coefficients. So this minimum number of experiments would be equal to 10. And the level, all of you know that minimum 2 levels, isn't it? If you want to vary the temperature, you should have 30 and 40 minimum. So if you can have 50, it's okay, but minimum 2 levels should be there for each variable we consider. And of course, there should be a full factorial combination for the experiment. What is full factorial? I will explain later. If you see that the first 8 experiments, this is the one particular experimental design. I think you would know the meaning of experimental design. That is, you cannot conduct experiment in any way you want. If you want to reduce the error in your prediction, there are standard experimental models available. One example I given is the Box and Hunter model here. So the Box and Hunter model is for the 3 variables. If you see the first 8 experimental combination, it is the full factorial experiment, full factorial. So the 2 levels for each variable are fully combined. All the combinations, whatever possible, are considered here. That's why it is called the full factorial. No combination is left out. So the other, the 4 points or the 4 experiments are the star points. You see that one variable is kept at the higher value or lower value. The other levels are kept at 0 for each variable. You could notice that. And the final important point is you see some replication from 15 to 20. If you see that from 15 to 20, the experiments are replicated at the central value. So whether you are familiar or not, And any statistical experiments, this replication is a must. Without carrying out the replications, whatever the equation we obtain, that may not be a valid one. So the replication of the experiments is essential part of any statistical experimental design. This is the standard model proposed by Box and Hunter. It is a very common one. And of course, once you design the experiment and conduct the experiment, you will have the measurements on the response. And using the method of least squares is all a mathematics part. You can estimate the coefficients. And now the equation is like this. I have given a very more generic equation. And it can be two variable, or it can be any number of variable. I given that. So you have estimated the coefficient beta. Beta is the original or true coefficient. In its place, you have estimated the value b. You all know the meaning of determining the beta and estimating the beta. Determining the beta is very difficult because you have to conduct experiments many number of times. That means infinity times actually. But with a small number of experiments, say the 15 experiments or something like this, I've shown that, isn't it? We can estimate the coefficient. And of course, after the coefficients, we can find out whether every coefficient is significant or not using some t-test. The insignificant coefficients can be dropped, and the remaining coefficients can be recalculated. Of course, the final equation, whether it is good or not, isn't it? We generally call it as the goodness of fit test. You have to apply F test and find out whether our prediction are involving less error. So you know that you can use the equation to predict the variable. And there is actual observation. So the difference between the actual value and the predicted value. So that is the error. So the error should be minimum. Whatever the equation we derive, that error should be acceptable one. If it is not acceptable, we cannot use the equation. So if you go by the methods proposed by the statisticians, and you consciously accept all those points and conduct the experiments, you will end up with less error. So that is the main objective of all this statistical analysis and the design of experiments. So from the equation we get, we can plot the contour maps. It's called contour maps. It's for two variables and gives a response. Maybe familiar, all of you may be familiar with this contour maps. So whatever the circle shown inside the graph is a constant value for the response. And x-axis is one variable, say temperature, another y-axis is the pressure. So the two variables, the effect of two variables are shown in a single graph. That's called the contour plot. And you can show them in a 3D graph also. So you see that this is the 3D representation of the equation, how the response varies when we vary the variables. As I said that you can go for optimization also. Optimization requires some mathematical analysis. You know that when you want to find the level of x that gives the best result, you have to partially equating the partial derivatives of the regression equation to 0. You will find out the set of x that will give the best value. So you may have three variables, say x1, x2, x3. So for each variable, you have to equate the equation to 0, and you have to go for partial differentiation. So, and you get the value that would give the best desirable results. And so, just to sum up, actually, I am in the first part of my lecture. I have given importance for the selection of the sample size. So the first part, I given the importance for the sample size. You all know that the sample size would decide the quantum of error you would commit in our observation. So we cannot escape or eliminate the error. Error would be always there in all our statistical analysis. I also told you what is the statistical phenomena, isn't it different from the deterministic phenomena? So all the statistical phenomena will involve in our observation an error. So to minimize or optimize the error, we should choose the correct sample size. The sample size is very, very critical. And the second part I told you about the experimentation that might be helpful for those who are doing research work. So any experimental design should be based on some statistical models. That's very important. And that will also again reduce the error in our prediction. So again and again, it is error, statistical error. We have to minimize the error. So to minimize the error, we have to carefully apply our statistical knowledge so that the error can be minimized. And so I will conclude with this statement. Thank you.
Thank you, sir. Thank you so much for your lecture. Not only for the lecture, sir, I would like to thank this giving us a free hand for organizing this STTP, and because of our Vice Chancellor, Registrar, Deputy Registrar, we are able to organize and we are able to innovate in our training programs. So thank you so much, sir.
Thank you.
Now,
I don't know
sir,
yes, please.
sir, you have to leave the session, sir.
Okay. Thank you. I cannot continue, huh?
No, sir, you can continue, sir. No, you can continue. You asked me how to leave, so I thought I